So when we are dealing with mesh, we need to ask ourselves certain questions. We need to ask ourselves whether the mesh is to be chosen in a way that we can have a very quick setup time, so we can generate the mesh as quickly as possible so that we can focus more on the analysis. We're not just stuck with the pre-processing part. As a matter of fact, actually this is what has been happening, that such pre-processing task is usually outsourced by companies who want to concentrate rather on the solver part, on the analysis part. But this is one of the questions we need to ask. What is the setup time involved in creating and generating such mesh? So structured mesh is very helpful. I'll show you a slide about what are the advantages of structured multi-block meshing strategies, how much it can improve the accuracy of the problem. But the other problem is that it is quite time consuming and it requires a lot of skills to be able to generate structured flow aligned mesh. Um, and it is possible on simple geometries, but on complicated geometries it requires a lot of time to set up the problem. So this is one of the factors we'll consider in deciding which kind of mesh we should go for. The other question we need to ask is, well, in structured mesh I can have great control over the number of elements, unlike an unstructured meshing algorithm. So I have to also ask how much computational effort will be required for me. So is my hardware able to handle such a huge cell count? For example, just to give you some numbers, if I have a mesh count of 1 million cells, then a 1 GB RAM cannot handle even a mesh for display purposes, leave aside solving the equations in the 1 million cells. So it's a very huge computational effort that we require. So we need to also handle these kind of questions before choosing what kind of mesh I should do the simulation on. Some of the in one of the important characteristics of a mesh is its quality. I can speak about quality in terms of the node point distribution and the valency of the mesh, or the smoothness and the skewness. I'll just explain this in a minute. This is very important to have a good quality mesh so that we can have a stable numerical computation and an accurate one. Ultimately, we want that the CFD analysis should correspond to the experimental results that we have. So in that case, the mesh quality needs to be taken care of as well. And what we need to be aware of is that the mesh quality can be defined in different parameters or different quality criterias, but some of the important ones are the node point distribution. So it defines how much the nodes are distributed within the domain. The nodes are the points at which the different elements join together at one single point. So it also includes a concept called the valency of the mesh. So it means if it's an unstructured mesh, the valency of a mesh can be varied. So usually what we expect is one node should be shared by same number of elements all throughout the domain. That is surely maintained in a structured algorithm of generating the mesh, but in an unstructured mesh it is quite possible that one node can be shared by a different number of elements, and that's one of the part that contributes to inaccuracies or instability of the numerical scheme. The other thing that we try to be aware of is the smoothness of the mesh. So we want a smooth transition of the elements. It should not have happen that a very small mesh element is attached to another mesh element which is quite big compared to it. So such sudden transitions in the mesh sizes can have an adverse effect on the stability and the accuracy. And in addition to this, we also need to be worried about the skewness criteria. So skewness can be defined as how much your given element, let's say it's a tetrahedral mesh, so how much is the tetrahedral elements in your domain differing from an ideal tetrahedral. If I'm speaking about an ideal tetrahedral, it includes a tetrahedral which has equilateral triangles as the faces which contribute to the overall tetrahedral element. So how much your element is deviating from a equilateral phased tetrahedral element, or if it's about, let's say, a 2D mesh. So an ideal quadrilateral or ideal triangle would be, let's say an ideal quadrilateral would be a square. So if you have a quadrilateral element which is more of a trapezium or a rhombus, in that case this is differing from an ideal element square by some skewness value. So it's a factor of something which is assessed in a scale of 0 to 1. So if it is 0 skewness, it means it's a very good element, it's very close to the ideal element which we expect. Skewness can be defined in terms of angle as well as sizes. And if it's close to 1, in that case it means a very very bad element in which you can have great problems with stability of your numerical computation. This factor of 0 to 1, this can vary from between the different software packages, but what is accepted in ANSYS Fluent is 0 is a very good element and 1 is a very bad element. So you should usually try to maintain a very good quality mesh from this aspect. Here is the concept of why one should go for a structured mesh. Although it is a great effort to generate a structured mesh, but we usually go for it just because of this aim. Here is an example where you have a backward step problem, and the other example of a backward step problem which has been meshed by unstructured elements. This is triangles using an octree algorithm without any boundary layer. Here you have a single block structured mesh which has been smoothed using orthogonal smoothing options. And what you can see here is that when the flow enters inside, the mesh is very much perpendicular. I mean, the flow is entering normally into the different elements. It is really closely following the mesh structure. The flow is closely following the mesh structure. So here you have the least numerical errors. So if you're speaking about discretization errors, this is least in the case of such structured multi-block meshes, because the flow is often aligned along the grid direction. But there are other kind of meshes like the unstructured algorithm based mesh which has been generated here. The flow never enters normally, it's hardly entering normally, so this will lead to a lot of numerical diffusion or numerical errors into your problem. Unstructured mesh, of course, it's useful because it's very quick to generate, and there are certain class of problems like combustion problems or some others in which the flow is very highly swirling, where the flow will hardly be aligned along the grid direction even if you maintain a structured multi-block mesh. But what you can see here is that a multi-block mesh gives us the flexibility to control the size of the mesh or the cell count, but unstructured mesh, it's often not so much under our control. So we should go for structured mesh because of two reasons: because of flow alignment and therefore reducing the numerical errors, and in the other case we also want to have a greater control over the mesh size. So these are some of the features why we go for a structured multi-block mesh. Let's have a look at another example of a sector of a combustor, let's say. And what you can see here is an L-shaped, L-grid type multi-block structured mesh which has been generated. And what you can see here is quadrilateral faces here which are getting extruded. So it's an L-grid type multi-block structured mesh. Unlike an unstructured mesh here. Now let's say if it's a combustor where the flow is not really aligned along the along the direction of the mesh, in that case it is okay to have an unstructured mesh using one of the good algorithms like octree or Delaunay or advancing layer methods or advancing front method. But at least what we should maintain here is a prism layer. Now what you can see here is, in this case, there is a very nice boundary layer which has been generated near the walls, unlike here there is no boundary layer, so this is bound to have a lot of computational errors and stability concerns when we are doing the simulation. So at least unstructured mesh, even if it's an unstructured mesh, at least to have a prism layer will be very helpful to have a robust and an accurate prediction of the flow characteristics. What Fluent can also handle is the non-conformal mesh. Now what you can see here is a non-conformal grid interface. So non-conformality means that the mesh elements are not exactly overlapping on top of each other. So you have two examples here, one in which they are exactly overlapping on each other, and in the other case they are only overlapping partially. So Fluent can also handle such kind of meshes. What it does internally is, like when you create an interface between the two interface zones, then in that case whatever is not overlapping, it will treat it as a wall, and whatever is overlapping will be treated as an interior boundary so that the flow can go through. And this is very helpful when we are, let's say we are giving the task of mesh generation to different engineers and they are generating meshes independently, and ultimately on our simulation environment in ANSYS Fluent we are merging all the different meshes, and we want to merge the meshes because it has been generated independently. So in such cases this non-conformal mesh interfaces can be employed. Usually there are some averaging errors which come into picture, because of which some industrial practices prohibit the use of non-conformal interface. They try to maintain as much as possible perfect conformality so that the flow can enter in without any averaging at the interface. One of the important things that we perform after we import a mesh is to check the mesh. So we check the mesh whether there is any negative volume. This is an important feature we often check ourselves for. So we check whether there is any problem with inverted elements, if the skewness is too high or if it's bad. And we also see some of the features like the domain extent, the grid topology, the number of faces, number of cells in different zones. So this can be done through grid checking. It's usually a very good idea to do this before we start the problem setup. Now, ANSYS Fluent has some terminologies associated with meshes, and it's good to know these terminologies. So some of the things are cell centers and nodes, which we will often hear. The node is the point, the corner point of a mesh element, and cell center is the one which is not usually visible, but it is the location at which all the data is stored. Fluent is a cell center based code, so it stores all the data, it evaluates all the data at the cell centers. You also have some edges which constitute uh, the given mesh, and a collection of edges constitute a face, and many faces together they constitute a cell. So in 2D and 3D this might have different meanings, but overall what you can understand is that we have these four characteristic terms associated with a mesh. A collection of faces is called a face zone. Now Fluent uses the term called zone or thread. Let's say this is the inlet face, that's the wall face, that's the outlet face at the other end. So in that case, a collection of these faces will be termed as an inlet face zone. And let's say I have two different domains, in one in which there is a solid domain, the other one in which there is a fluid domain. In that case, a collection of cells is called a cell zone. Now this is very helpful. It's also called a thread. Whenever we are operating with the Fluent's source code, it calls the zones as thread. So it's helpful to know this when we are writing the user defined functions. When we want to access data within a cell zone, in that case we have to access its thread ID number. Let's have a look at the features which are available in ANSYS Fluent. Variety of features, very many of them. So Fluent can solve problems in two dimensions with planar axisymmetry, also with swirling flows which can be approximated using a 2D axisymmetry geometry. It can also take care of 3D flows, and it can handle a variety of mesh types as has already been seen. We can handle both steady state and transient flows. So even if it's an unsteady flow, we can take care of it using the appropriate schemes, time marching schemes. It can handle both incompressible and compressible flows. Fluent has special features to capture highly compressible flows using its density-based solvers, by which you can capture really hypersonic flows, very high Mach numbers as high as 4 or 5, and higher even. And it can deal with the viscous effects using either an inviscid flow solver, which is basically an Eulerian solution to your problem, or a laminar flow in which the viscous effects are taken into account. And in another case, if the Reynolds number are a bit higher, or the Rayleigh number is quite high for a natural convection problem, we can also have a turbulent flows being modeled according to some specific turbulence models. A variety of turbulence models are included. I'll speak about this dedicatedly in the lecture on turbulence modeling. Fluent can also handle heat transfer options, and a variety of heat transfer options for solid fluid, conjugate heat transfer, or within the fluid, natural convection or mixed convection or forced convection. Fluent can also deal with multiple species. So you have a single phase, let's say air, which has multiple species, oxygen, carbon dioxide, nitrogen, different species within a given phase. And you can also deal with user-defined scalars or additional variables, so you can solve additional transport equations as per your requirement. These are some basic modeling options in ANSYS Fluent, but it also has some advanced modeling capabilities in terms of special kind of heat transfer modeling, like solar load model. You can include the solar load, that is the position of the sun if it is exposed, if your geometry is exposed to sun at a specific time. You can include you can mention the specific date, specific time, and the hour exactly, and you can get the necessary load at your specific latitude and longitude. So it's very helpful to include also solar load models, especially for cabin control, cabin cooling, or cabin heat transfer modeling for HVAC applications of cars and automobiles. And you can also have radiation heat transfer modeling. And Fluent also offers the option of modeling moving reference frames or multiple reference frames, sliding mesh models, dynamic meshes. You can do IC engine simulations or flow induced rotations, degree of freedom, 6 degree of freedom kind of simulations can also be performed. You can also modify your equations by including some extra source terms, either as constants or user defined. And one of the important things of ANSYS Fluent is its multi-phase flow modeling capabilities. You can also include combustion or other kinds of reactions within your flow, and there's a huge variety of material database to be accessed in ANSYS Fluent. So there are a variety of options available in ANSYS Fluent for analysis, and it's very quite popular because of these many features. We'll have a look at how we can access help in ANSYS Fluent. So you can anytime on the GUI you can click on help at different locations. So if a control panel is open, you can go to help here. You can access help of Fluent directly from the menu bar, and you can also access help within the features which are visible on the control panel here. Embedded help is there, so if you click on this, the help for that specific control panel or features come into picture. But you can also go to the general user guide index by which you can access the different kinds of options in Fluent help. So since 13 release, as we see it here, it's an integrated help. It's included with other ANSYS help manuals within one single environment, so you can get a huge number of options for accessing different Fluent help pages. So you can start with user guide, which defines you how you should navigate through the panels, how you should set up simple kind of problems or complicated problems, multi-phase problems. It helps you. It's a guide for going through the setup of different kinds of problems. You can also have a theory guide, so you can see the theory behind the multi-phase problems. You can also go to a tutorial guide. I'll just show you this in the next subsequent slides. So if you see here, we can click on the control panels, and if you click on help, then the description of that specific control panel comes, and there are also hyperlinks associated with the theory guide or the user guide included embedded within this help manual. And you can also see description of specific models in the theory guide of ANSYS Fluent, or the specific way in which you should usually set up a shear stress transport or other kinds of modeling features, how you can use them. And the theory guide describes to you the equations involved. So let's say it's a species transport problem. It tells you how the mass fraction equations are solved, what is the transport equation included, what are the source terms, so that you can understand it better. And it's also very helpful for a basic understanding of the problem. In addition to this, it's very helpful to go to the tutorial guide. So this is another section in ANSYS Fluent. The tutorial files are usually accessible through the customer portal. So this is the link for the customer portal from where you can get the necessary mesh files, and you can use them for doing simulations following this procedure as described here. It describes the complete setup of the problem, and you can start with the first tutorial in case you are interested to learn Fluent. So all these things will become very clear if you go through the first tutorial. It expects that you are not knowing anything, and it will guide you through the complete process of setting up a problem in ANSYS Fluent. So as we can see here, ANSYS Fluent is quite strong, and we should be familiar with some specific things like the file formats, how we should deal with the unit system in ANSYS Fluent, that internally it is an SI unit system. So if we are interacting with the source code through a user-defined function or through a profile file, we should be aware of this, that all the inputs need to be given in the SI unit system. And you can choose the appropriate mesh for efficient, accurate simulations. A structured multi-block flow aligned grid is the best choice, but it's complicated to generate it. Usually with the hardware that is available here, we can deal with very fine unstructured mesh and rather concentrate more on the solution process and the analysis part. There are certain features for mesh modifications in ANSYS Fluent, but usually such things should be done at the pre-processing step, and we can check for help on any things regarding theory or specific topics, or help concerning the setting up of a problem. We can always access on the ANSYS Fluent GUI. So I hope you could follow what are the things we need to be aware of before we start off with simulations. Regarding ANSYS Fluent, I hope you could get a bit more of an overview of what it would look like when once we start with performing a simulation in ANSYS Fluent. And anything that you require help regarding these topics, you can always respond to this email ID which is provided on the page here. I hope you enjoyed this lecture and stay tuned for the next ones that are coming. Thank you very much for your attention.